Good. Then the second talk is on algorithmic information design in multiplayer games, and it's given by Haifeng.
Thanks, Martin. Hello, everyone. I'm going to talk about algorithmic information design in Singleton Congestion games. This is actually a work led by my undergraduate student, Chenghan Zhou. She's actually currently in transition to Princeton for graduate study, but due to visa issue, she cannot come in person, so I'm presenting here. This is a joint work with Thanh Nguyen from University of Oregon, and I'm Haifeng, originally at UVA, and recently moved to University of Chicago. Okay, so this talk is about information design, also known as Bayesian persuasion. In general, you actually have already seen an example in the previous talk, but in general, the goal here is to design the information structure of a game. That is, designing which player knows what, so that it can induce a desirable equilibrium outcome. In the past few years, there has been a lot of study about algorithms for optimal information design. And those results roughly can be divided according to two different dimensions. The first is about the types of scheme that you're going to design. There were typically two types. Either it's public signaling, which means you have to reveal exactly the same information to everyone, or private signaling, which means you're allowed to reveal different information to different receivers. So another dimension is roughly about the complexity of the setup you can consider. So this ranges from the most basic setup. There is only a single receiver, or in this case, of course, public and private signaling the same thing, because there's only one person, and to the slightly more complicated case with multiple receivers, but they do not have externality among each other, meaning one receiver's action would not affect another receiver's utility. And then finally, to the most general setup that the receivers are playing a strategic game. And in this case, your information will affect the Bayes-Nash equilibrium of this game. So in the past 5 or 6 years, there has been a lot of study for the first two basic setups. And so far, the algorithmics, complexity of those problems are reasonably well understood. But for the most general case, when the receivers are playing a strategic game, there has also been a lot of study, but mostly focused on the public signaling. And moreover, in some special classes of games, such as zero-sum games, VCG auction, or non-atomic routing. Actually, so you might have seen another very interesting talk yesterday on non-atomic routing for public signaling. By the way, this list is by no means to be complete, so I cannot fit everything into the table, so I'm just listed a few here. Okay, and there is a common feature for those games that has been studied, and that is those games all have a unique Nash equilibria under public signaling scheme, and that can kind of significantly simplify the analysis when you're trying to study the signaling scheme. But interestingly, so far, there has been almost no algorithmic result about the optimal private signaling in a strategic game. Okay, so what is this paper about? Well, I view the contribution of this paper mainly as twofold. First is we're trying to fill in this kind of empty space about optimal private signaling in a strategic game. And second, we're trying to develop some kind of new algorithmic concepts and techniques that can address games with non-unique equilibrium. So when your game so hopefully, this text can be applied to settings when your game do not have a unique Nash equilibrium. So here's the outline for the rest of the talk. I'm going to start by describing the game model and setup that we consider, and then I'll tell you the results we have. In this paper, we consider pretty much the simplest possible setup with externality and among agents. That's the Singleton Congestion games, which turns out to find a bunch of nice applications on the internet. So in this talk, I'm going to focus on one of the most popular and also natural application, which is ride-hailing platforms. In this game, you can think of it as you have a bunch of agents. Well, you can think of them as the drivers on the ride-hailing platform, so they're agent 1 to n. And there are a bunch of resources, which are basically the locations within the city that the driver is trying to pick. So every driver is going to pick one location to go and pick up a passenger and hopefully get some reward. Right? And different locations, of course, have different demand of the ride requests. Right? This naturally forms a congestion game because when multiple drivers go to the same location, they will be competing for the demand, and therefore the reward will decreasing as more agents come. And to kind of make it more concrete, let's kind of set up some very simple reward function that kind of depends on how many drivers at each location. Here, I pretty much choose the simplest possible demand reward function. And as you can see, when your demand is very low, as the theater case, your reward is always 0, regardless how many people are there. When your demand is kind of medium, your reward is always 2 epsilon for some small epsilon, regardless how many people are there. The only non-trivial location is the middle one with a lot of demand. And in this location, you will get a high reward 1 as long as there were not too many drivers there. So if there were n strictly smaller than capital N, then you always get utility 1. But once you get a lot of driver, that is n equal to capital N, your utility suddenly decreases to 3 epsilon because there's a lot of congestion there. And again, so our paper works for general demand, any actually arbitrary reward function, but here for the presentation purpose, I just make it the kind of simplest possible for the intuition. Okay, good. So, and as you can see, this middle location turns out to be the most rewarding location because even in the congested case, when everyone goes there, you still get 3 epsilon, which is larger than the left one, which is 0, the right one, the 0 one, and the 2 epsilon one, right? And therefore, it's very natural that everyone going to go to the middle location. They didn't get the ideal reward of 1, but they do get 3 epsilon. That's kind of the equilibrium you can expect. Okay, so far so good. But the interesting thing here is, in reality, typically only the platform can observe the demand. But the driver is actually uncertain about the demand for different location. Maybe what we see here is just the one possible state of the world, which let's say happens with probability half. Maybe another possible state of the world is actually the demand of the first 2 locations switched. Therefore, their reward function also switched. And this is uncertain to the drivers because they only have some prior belief, but the platform can observe this exactly. So the information design problem we look at is, as a platform who can observe the demand information, how can you strategically reveal this demand information so that you can influence the driver's behavior and therefore maximize your welfare at the equilibrium? And intuitively, in this particular example, roughly what you're trying to do is you're trying to satisfy the demand at the high demanding location, but meanwhile try to avoid the congestion by strategically reveal information. I want to just quickly highlight that those kind of signaling schemes are not imagined by me. They actually already exist in the real world. If you look at platform like Uber, you can, from the driver's perspective, actually Uber is going to show you the search price or maybe the multiplier for each of your trip. And these are exactly the information that Uber reveals to the drivers in order to influence their location choice. So what we're going to do next is we're going to see how you can reveal those information optimally, how to do it optimally. Let's try some simple kind of idea. So the first thing you might come up is, why don't we just be transparent, right? I'm going to just reveal the demand information completely to everyone, transparent. Does this work? Well, as you can see, in this case, if everyone knows the most rewarding location, and then they're going to just everyone pick the location, and you get 3 epsilon, and in total you get 3 epsilon times n for the welfare. So generally, it turns out that it's typically not a good idea to be fully transparent. In this particular example, it turns out that there's a very simple scheme which turns out to be private, which means you have to reveal different information to different drivers that achieves optimal utility. And the scheme is pretty simple. Basically, you're going to reveal full information to all the drivers except some kind of randomly picked driver n. Okay, so there's one guy who doesn't know anything, but everyone else knows everything. And it turns out that for every driver who gets the full information, they can exactly know which location is the most rewarding, so they're going to go there. And that turns out to be a dominant strategy because you cannot do, if you know which location is the best, that's your best choice. But for this only pool driver who was randomly picked, he cannot distinguish the state 1 and 2, which makes the best response for him is to go to the last location, which is the grocery place. He gets 2 epsilon. The reason that he go to the last location because once he joins the competition, then he will become the nth player who suddenly drives the congestion very high and hurts everyone. And that's, that's kind of, this kind of toy example illustrates the rough intuition that why information can help you to coordinate the driver's behavior and reduce the congestion. And it turns out that in this case, their total welfare is n-1 plus 2 epsilon, because those n-1 person who have the full information, they would enjoy the reward 1. Okay? Well, now you might wonder, your scheme seems to require to send different information to different drivers. What if you are restricted to send exactly the same information to everyone? Maybe due to some fairness constraint. You say, there are regulations saying you have to be fair to everyone. And in this case, I'm not going to show you the detail, but it turns out that you can show the optimal welfare you can achieve is 2n divided by 3, which is much worse than the previous one, but still significantly better than your transparent policy. Good question so far. Yes?
If you're giving the same information to all the drivers, that means you're sending a public signal.
Yes, that means send a public signal. Meaning you reveal exactly the same thing to everyone, but doesn't have to be transparent. You can be strategic, but it has to be exactly the same to everyone. Yes?
Very curious. Can you briefly describe what the public signaling scheme against that is? So I think you're going to mix the good state with 2/3 with the bad state 1/3. That's kind of the optimal public signal. But we can chat more about that offline. Yeah. Good. Okay, so this leads to the formal model of the problem, which is the following. Essentially, just an abstraction of the model I described before, except that we're going to allow arbitrary reward function, and the state is drawn from some discrete distribution. And one thing I want to emphasize is that this didn't show up in my previous example, but in general, the game actually have multiple, actually possible exponentially many equilibria. Okay, next I'm going to describe our result. So in a nutshell, this paper basically is about the algorithms and the complexity of optimal information design in the singleton congestion games. Our result can be summarized by this table. We study both public and private signaling. And it turns out that the number of resources turns out to matter a lot in this case. And we show that when the number of resources is small, we can have a polynomial time algorithm for both public and the private signaling scheme. But when the number of resources goes too large, we show that both are actually hard. In particular, the public signaling is equilibrium obliviously NP hard, which is a new notion we introduced to capture hardness of signaling when your game have multiple equilibria. So for the rest of the time, I'll quickly go through this two results. So let's get to the first so the possible result about polynomial time algorithm for optimal private signaling. And there were roughly two steps to handle this. The first is by reducing the optimal private signaling to a problem called optimal correlated equilibria. And this is due to a very nice characterization by Bergman and Morris, who showed that the set of all the possible base Nash equilibria that can be induced by signaling scheme is exactly the set of the base correlated equilibria. And with this result, because we can simply focus on optimizing the base correlated equilibria. But this doesn't dramatically change the complexity of the problem, because it's well known that optimizing correlated equilibria is a very well-known difficult problem, as being studied previously in a few seminal works. The key challenge here is that a correlated equilibria need to optimize over exponentially many action profiles, because every driver needs to pick an action. So in total, the total number of action profiles is going to be exponential in the number of drivers. And that comes to our kind of key technique, which is instead of working with this entire action profile, which are too many, we're going to work with some kind of reduced form of the base correlated equilibria. In particular, if you recall, in a correlated equilibria, each agent, when he was assigned an action, the agent need to infer the posterior distribution of all the other agents' actions. And that, so this kind of the action of those. And fortunately, it turns out that in congestion games, that we only need to care about the number of agents at each location, because that's the only thing affecting the agent's utility. And therefore, our reduced form is basically the joint probability of the congestion at every location, jointly with the assignment of some kind of agent n to the resource k, plus the random state of nature theta. That's kind of the joint probability of everything here. The key technical challenge here is when reduced, so there are many possible vectors of this kind of reduced form. Which of them are feasible? That is, which of them can be implemented by a signaling scheme? So that's not clear ahead. So what we do is we designed a network flow-based analysis which can characterize the set of all the reduced form that can be implemented by signaling scheme. And then we can optimize over those reduced form. So next, I will quickly mention our negative result, which is the equilibrium the hardness of signaling for games with multiple equilibria. So the key challenge to handle here is when your game has multiple equilibria, how do you prove a hardness result? One natural thing you're going to say is why I just don't pick a particular equilibria. For example, the typical choice, you're going to pick the most optimistic or most pessimistic equilibria. But this actually turns out to be problematic if you want to prove a NP hardness result. The reason is because you cannot disentangle the hardness of finding the specific equilibria from the hardness of signaling. For example, let's say you prove that it's NP hard to find a public signaling under optimistic equilibrium tie breaking. But then how do I know your hardness comes from finding this particular optimistic equilibrium or comes from the signaling problem itself? So to address this challenge, we introduced a new notion which we call equilibrium oblivious in approximability. In particular, we're going to say it's equilibrium obliviously NP hard to find an alpha approximation for your problem if it is NP hard to find a scheme pi that satisfies the following condition. That is, the objective of your pi under the best possible equilibria is at least the alpha fraction of the maximum objective under the worst case equilibria. In other words, your algorithm is privileged with the best equilibria, but our benchmark is disadvantaged with the worst equilibria. But even in this case, you cannot guarantee your algorithm have an alpha fraction of the optimal. And our main result shows that it's equilibrium obliviously NP hard to obtain a 1 - 1 over 5n approximate equilibria for welfare maximizing optimal public signaling. And this is a very convincing hardness result, showing that it's going to be difficult regardless of what equilibrium selection rule you choose. Finally, I just want to briefly mention a very interesting open problem, which is the complexity of the private signaling. In this paper, we show that the separation oracle for the dual problem of this one is NP hard, but we don't know what's exactly the complexity for the original problem. And with that, I will conclude, and thank you, everyone.
Thank you very much. Questions?
So the part, can you go back one slide?
Yes.
It only rules out the FP-TAS, if I'm reading it correctly.
Yes, you only ruled out FP-TAS.
What do you think about the p-TAS then?
That is a good question. I'm not sure. I think, yeah, actually I tried to get a constant hardness, but I was not able to. Yeah.
What you're saying is your construction for this result?
Yeah, my construction doesn't work, yeah. That's
right. So I think you're using like worst case reward/delay functions in this hardness reduction, aren't you? So do you think there is like hope for, if you go for like congestion games with linear delays, quadratic delays, like, do you think there's a way to sort of obtain positive results for certain classes of games?
So linear delay is definitely very interesting. So that actually reminds me the paper that you had yesterday. So that's a very interesting question, I think. I'm not sure whether linear delay we can do anything positive here, or even prove that full information is optimal. That's a very interesting question. But quadratic delay is very difficult. I remember I worked on that before. Actually, a couple of years ago, I tried a lot of ideas, but quadratic delay is very difficult, I somehow feel. So yeah, but actually the hardness construction in our paper was not a weird function. Okay. It's I think it's inverse polynomial, 1 over n, some things like that.
More questions? Online questions? Okay, then let's thank Haifeng again.
Thanks, Martin.